Unmute, share screen. Okay, theoretically these guys can get back in again, and there they come. Okay, good. All right. So I'll wait a few seconds because there were 11 people, and we'll see how many of them. Oh, 6 of them, 7 are awake. Okay, good. They're mostly awake. All right. So let's find the Kahoot about DES part 1. This is it. Okay. Good. 9 people are back. Most people stayed awake. All right. So the number is 921, 652. Good. There they come. Good. Stupid. I like password. First time password 1, I actually didn't write down the name. I thought there wasn't a name. It fooled me. All right. Wait a few more seconds. Looks like we got everybody. Okay. 5 questions. What type of cipher is DES? Okay, it's a symmetric block cipher. Good.
It is block, sure.
All right. Which of these is too weak to use now? I'm going to have to mute the online people again. I'll wait till after the Kahoot stops to do that. All right. DES is too weak. That's good. Let me just mute these guys. Now that I know how to do it. Good. All right. All right. That will stop them from irritating one another. All right. So that's DES is no good. Good. All right. Which operation creates confusion? Okay, substitution creates confusion. Substituting characters with others makes it so the result is not obviously related to the key. All right, which of these is a product cipher? All right. Okay, DES is product cipher. So is AES. All right, how long is the key? We should all know that. There they come. "56 bits, good, all right. So it's NH, stupid, and DH. Okay, all right. So I think we got 15 minutes yet. Let me just go a little further here. And all right, so here's the components of DES. And I thought it was kind of funny. I went through this recently in the capture the flag network. They had a 5-cell network you had to figure out. So a 5-cell network is how it works, which is kind of insane. What you do is you take 16 bits of data and you break it up into 8 bits, 64 bits. You break it up to 32 bits and 32 bits. You have the left 32 and the right 32. Now you take the right 32 and use it to make a key, which you then XOR with the left 32, and the right 32 is just passed through unchanged. So you only encrypt half the bits, and you use the other half of the bits to create the key to scramble the one on the left. So one round of encryption only scrambles half of the data, which is kind of nuts, but that's how it works, and that's why you need so many rounds, and that's why at the end of the round you flip the left and the right, so the other ones will get encrypted in the next round. So you have 16 rounds, which means each half of it gets encrypted 8 times. And the other half of it, other 8 times, it's used to create the keys to encrypt the other parts. So you're going to find this is true of almost every modern form of encryption. You somehow take part of the stuff you're creating to create the sort of random entry that causes the next round to work. There's different things like cipher feedback and cipher block chaining, where you take the output of one round and you use it to try to make the next round as effectively randomness going into the next round, although nothing is random, of course, because if you know the key, you can totally reproduce it, and you have to decrypt it. Yeah. Having it split in half is what makes it a Feistel network, where only half of it gets encrypted and this half is used for the other. That's this strange thing. Feistel is apparently an important cryptographer, invented this stuff. Yeah?
So what if it's 16 bits, right?
The input is 64 bits, and you break it into 2 32-bit words. And you use one of them to help create the key, and the other part gets encrypted.
What if the message doesn't take up 32 bits?
This is a really important question. What if it doesn't take up 32 bits? All block ciphers have a fundamental limitation. You have to fill the block. So if you try to encrypt anything that is not long enough, you have to add padding to make it the right size. They don't work at all unless you have the right size of input. So you have to have an integral multiple of 64 bits. So if you try to encrypt a message that's only 5 letters long, it will add 3 bytes of padding. And that turns out to lead to a lot of horrible attacks called padding oracle attacks, where you can, because the padding is not random, you can deduce something about the key. There's a whole series of the Beast attack, Lucky 7, the crime attack. There's a whole series of them based on this problem. That's the weakness of all block ciphers, is you somehow have to fill the block. And whatever you fill it with becomes something that can be exploited by the attacker. Yeah.
Is the spec says what you pad it with?
What there are, you ask me what do you use to pad it with? There are 3 or 4 systems proposed. The one that's most commonly used, you could just pad it with zeros, but the most common thing is to pad it with bytes that say how many bytes you're filling. So if you're filling 10 bytes, you fill it with 0A bytes. If you're filling 11 bytes, you fill it with 0B bytes. That's the typical way it's done. But there are 3 or 4 padding routines. We'll get to them later, and none of them are perfect. Just the fact that you're padding it creates a certain amount of weakness. Good. All right. So that's the game. You only encrypt half of it every time, but every other time, the other half gets encrypted, so they both get subjected to several rounds of encryption. You do this 16 times. You have 1 permutation at the start and 1 at the end, and that's DES. And as I mentioned before, these systems are designed not only to be secure, but also to be fast on real hardware. They're designed for computers, so you don't do any operation that isn't easy to do fast on a computer if you can avoid it. All right, so left and right are flopped again at the end, and they're followed by a final permutation. And the permutations work like this. Remember, you have 64 bits. So you're just going to scramble the bits. So you put bit 1, wherever 1 is in this mess over here, put bit 2 up there, bit 3 down here. You just take 64 bits like a chessboard and move them around. That's how you create the diffusion, I think. And that's the permutation. The initial one is here, and the final one is there, and this one undoes the other. This is just a way of scrambling the bits. So patterns are removed. Yeah.
So are these blocks fixed?
Fixed, absolutely. And published. They never change. That's right. That's how, otherwise, it totally wouldn't work. So you always scramble them in this fashion, and you always, at the end, you always scramble them in that fashion, and therefore you can undo it. It's not random, and it doesn't depend on the key. All right. So then there's that called the F function. This is the main operation. You have round and key. You expand it. You XOR with the round key. Then you go through a substitution and then a permutation. This is what the 4 steps of each round are. The expansion creates a diffusion. Go through some kind of expansion matrix here, which again just scrambles the 32 bits. Again, a similar thing here. Then you XOR it with the round key, and then you run it through the other yeah.
For a previous slide, the initial permutation, the final permutation.
Yeah.
Again, the final permutation is the inverse of the initial.
I think it is, but I'm not quite sure. It's not obvious to me. It doesn't look like it though, because the 1 is way over on the right here and the 1 is on the bottom here. I don't think the final is the inverse of the initial. They're carefully chosen, to create the right bound diffusion. To undo it, you just have to run the whole thing backwards. So this is not, the final is not the inverse of the initial. It's just a different scrambling feature. And to undo it, you're going to have to reverse it knowing that matrix. But I'm not sure about that. Yeah.
On the author's video,
Yeah.
the notation -1 means inverse.
Oh, it does mean, you're right. It does imply that it is the inverse. You may be right. It may be the inverse. The fact that it's written down -1 makes me think it is in fact the inverse. Yeah, okay. Oh, good. Well, thank you. Good. Don't let me get anything wrong, but you're quite correct. What you put into 50 gets moved to 2, and then what you put in 2 moves back to 50. Good. Thank you. So it is the inverse. Good. The purpose is to create diffusion, I think, so that each bit of input is smeared out. That's right. But the idea is, I know how to work if you're cutting up food. You cut it up this way, then you turn it and cut it up that way to make hash. That's what you're doing. You're taking the bits and scrambling them up, then encrypting them, and then unscrambling them. But the result is the effective one bit is now mixed among all the bits. That's what you're creating. You're creating diffusion. So if you change even one bit on the inside, it affects everything. It moves through all 64 bits and affects them all equally. That's the idea. And that's how you create it. And you'll see the same thing in AES. These are good questions. So there's an expansion function, which is similar, just moving the bits around. And there's a round key. So you have these 16 round keys, and you XOR them in, and you make them in the key schedule, which we'll talk about. So then there are these S boxes, and the S boxes are also carefully chosen, and they never vary. And they're listed in the book. I don't think I have them all here, but they're just a series of S boxes, these exchange boxes. Use these certain, which is, of course, very good for computers. You just make a matrix, you just look them up. You scramble things in a certain way, and it turns out to be the right thing to do. So you put in, now remember, you had only 56 bits of key. So what you do is you remove the parity bits, and then you move the bits around like this, and you create 32-bit keys. You're going to create, 48 bits. You select a subset, 48 bits of the original bits, and choose them by these schedules. And all you're doing is rotating little sub-bits. Like here's 4 bits, and you rotate them around and rotate them around. So you're just taking the bits and moving them around to create these different keys. The 16 round keys all come from the input 56 bits, and they're not modified in any complicated or difficult way, but they're just scrambled enough so that they make different keys for each round. Yeah. Yeah.
On the very bottom, it says C16 factorial or just exclamation point?
Just an exclamation point.
Okay.
That can't be a factorial. Yes, not a number. Very good point. That's not a factorial. All right. Yeah, but that C16 is the 16th. No, you're right. But the C could be, in principle, you could have a number called C sub 16, and that would be factorial. But that's not what it is. No. There are no factorials in this. That would be way out there. Be way too big. All right. So anyway, only the key schedule has to be modified for decryption. You run the same thing through in the same order, but you create the keys in the opposite order, and you decrypt. Because remember, it's an XOR operation. So all you have to do is another XOR the same key to undo it. So all you have to do is run the key schedule backwards, and you go through 16 rounds, and you will undo it. So that's the game. And I don't plan to get too deeply into the math because, like I say, that's where the mathematicians go. All we have to understand is how it works and, in general, what's going on. And all you're doing is trying to, just like cutting up hash. You cut it up this way, you cut it up that way, you stir it around, then you cut it up again and cut it up again. You're just trying to mix those bits so that all the patterns are gone. So even if the key was something really obvious, like all zeros, you can't tell anymore. Even if the input was something obvious, like all zeros, you can't tell anymore. You just see random junk coming out the end. But it has to be completely systematic so it can be reversed. No randomness is allowed. So that's the game. So here's the security analysis. There were 2 criticisms raised of DES. The key space is too small, and some people wonder where they got those S boxes. The S boxes are just these patterns of how to scramble the bits, and they just came from the NSA, who at this time, by the way, wouldn't even admit they exist. So the National Bureau of Standards said, we have these boxes, use these boxes. And people said, why should we use those boxes? They said, shut up, we can't tell you. And this didn't please people. They wanted to say, what is the logical mathematical argument for using these boxes? And we would not defend them. Anyway, it turned out that analytical attacks were very ineffective. There's been no analytical attack ever that breaks DES. You know, if you have something like WEP with 128 bits, you can never get in by brute force, but there is a defect in the math, so you can actually get in with something like 2 to the 20 guesses instead of 2 to the 128 guesses. That's what analytical attacks do. You find some clever way to do it so you don't have to try all the keys, and that has never happened with DES, even with all this time. The only thing wrong with DES is there aren't enough keys. 2 to the 56 is not enough. You could just try them all. And there never has been a better system than just doing 2 to the 56 calculations, which turns out not to be that difficult. So here's the attacks. Diffie and Hellman tried to estimate how difficult the attack would be in 1977. By 1993, people thought you might be able to do it for $1 million. And in June 1997, it was finally broken. I got a book about this. It's kind of fun. The book is named Brute Force. It describes the original brute force attack, which was done on the early internet in the 90s. Thousands of Linux server administrators, often without their boss knowing it, volunteered their machine to be used for 4 months as this giant attack. And they broke the thing up in all these little key spaces, and each of you would run on your Unix server some thousands of encryptions and then forward it back to the main server to see if you found the key yet. And after it took 3 or 4 months with the whole world working together, and they cracked a key by brute force. And that's why, you know, you could say that the NSA and the NBS were not the dirty, rotten bums you might want to say they are. It really was essentially impossible for anybody to do this until 97. And probably the NSA could do it in 77. And that's where one of the data points we go from when we say the NSA is 20 years ahead of the rest of the world. They apparently had something that could do this in the 70s. We didn't get it until the 90s. Anyway, by 98, they broke one in 39 days, and by 99, which when the EFF in San Francisco got in, and they built a special computer just for this purpose, and that one could crack the key in just a couple days, 56 hours. And then by 99, they could break it in 22 hours, and on you go. And in 2006, there's one that can do it in 6 days. So, you know, more and more devices. This is Deep Crack. That was the EFF's box. Each one of these racks is full of boards, and each one of those boards has a whole bunch of Deep Crack chips, which are special processors just to calculate DES as fast as possible. That's all they can do. And this thing cost, what, $500,000 or something, $250,000. And this thing could do a brute force attack in a few days and find them by just trying all the keys. Here's the one their textbook authors made called Copacabana in 2004 with all these boards, which I think are like graphics boards, doing DES super fast, and it can find the key in something like 10 days. And I think it was a whole lot cheaper. Copacabana was only $10,000. That's why it was an improvement. It was 25 times cheaper by 2006. So DES is broken. Nobody can trust it. For your mere $10,000, you can get in a couple of days, and that's not out of anybody's reach anymore. And besides, that was 2006. Now it's been another decade. You could probably do it for $1,000 now with a normal graphics card or something. So here's the alternatives. When it was cracked and the government was humiliated into being unable to defend it, the immediate recommendation was right now switch to triple DES. While we have a several-year process of choosing a new encryption standard, which will eventually be called AES. And so they said, yeah, if you want to be safer, just run DES 3 times. The simplest way to do it is just encrypt at key 1, encrypt again with key 2, encrypt again with key 3. That's the obvious way to do it. If it's not, now there are some things like XOR, when you do them twice, it doesn't get any safer, but DES is not like that. Another round of DES does scramble it more, especially with a different key. And another round with yet another different key scrambles it. So if you do that, it'll obviously take 3 times as long, but it'll be a whole lot more secure. And so it is. Here's another alternative. You encrypted DES with key 1, you decrypted key 2, you encrypted key 3. That's the version that's actually used by most hardware, because you can set key 1 equal to key 2 equal to key 3, and then it turns into single DES, so your hardware has a legacy mode to interact with your old equipment running single DES, and it has a more modern secure mode, which does triple DES. And that's what you always go for. Like I mentioned before, Microsoft Windows domain controllers have the same property. You install a domain controller, it's always much more secure, but it has a legacy mode saying if you want to mix this with an old domain controller, it will work. But it will, of course, only have the security of the old one. Or you can put it in native mode and have the security of the new one, but then you have to upgrade all your domain controllers to be the new one. And that's reasonable, and that's what this triple DES does. It gracefully degrades back to the old version, or goes up to the new version, and that's what people need as they're going to be replacing their hardware gradually to upgrade to the new and better system. All right, lots of people are still using it. By the way, another thing people do to make it stronger is key whitening. You get 2 additional 64-bit keys, and you XOR the plain text with a key, encrypt it, and then you XOR the ciphertext with the key. And if you think about it, this means just one round of XOR means if you're trying to guess all the 56-bit keys, now you've got to try another 128 bits of random key. You need another 2 64-bit keys to figure anything out. So even though you just do something very simple with them, there's just a bunch more keys to guess now. So you've effectively made it impossible to brute force in a very simple way, and they call that key whitening. So here's the modern alternatives. AES is, of course, the best. That's the worldwide standard approved by the government based on the RIN jail cipher, 128 bits and longer versions. And that's fine. Triple DES is fine, effectively 112 bits. And there's all these other ones we'll talk about more, but these are the finalists to the AES competition. Mars, RC6, Serpent, Twofish, and IDEA are all, for all practical purposes, just as secure as AES. They're just not the one that won and became the standard. Not that there's anything wrong with them, they're just not the one that was chosen as the fastest and best. So the political anarchist types would probably prefer to use them because they would have the cynical attitude that the reason the government approved AES is because they found some way to poison it, which might be true. Yeah.
I was about to ask, like, should potential security analysts run these equally to see if AES is poisoned or not?
Yes, the question is, should people be analyzing AES to see if it's poisoned? And obviously they should, and they are, and no one's ever found it. But there are persistent rumors. Another persistent rumor I've heard for 15 years in this business is that there's a secret password that will get in every Windows server, a secret account. No one's ever found it, but the rumor persists. And it's hard to ever prove, but absolutely. And every now and then they do find backdoors. They found backdoors in a few crypto systems. Every few years, they seem to find another backdoor in one of the famous crypto systems people are using. So that has really happened 3 or 4 times that we know for sure, that the government has put a secret backdoor and stuff. And now the FBI and the cops and everybody, the Department of Justice, are all very strongly demanding backdoors and everything. So there's a lot of pressure to do it, and I would assume some people are doing it. Anyway, so that's this stuff, and I got another Kahoot. I think I'll wait till after we take a break for this one. Let's pick up at 10 after 7. We got this and a little bit more math. I'll do the XORs today. And so put your name on this so I know you're here, just so I can tell the bean counters what the attendance is. I'm going to stop the share and start it again in 10 minutes.